All right, so this is, I hope you're familiar with this look. This is the review document for Chapter 10. And there's a separate one for Chapter 11. This is organized by easy problems first, moderates, and then difficults. And I've since discovered that in at least one case, an easy question should have been put in the moderate or difficult, but it should become obvious once we get to it. But I've got some marked off here that I want to get to for sure, unless you have found one or more of these review problems that gave you trouble, and we can deal with those right now. So we be sure and not run out of time and answer your questions first. Otherwise, I'll kick it off with number one. So for the benefit of our later viewing audience, this is Chapter 10. Okay, and this is the easy group, number one. Which of the following should have the lowest boiling point? So what do we need to know? Excuse me. What do we need to know to answer this question? We need to know what are the forces that are holding the individual ions, molecules, whatever the case may be, holding them together. Because boiling is a physical process. It's not going to break up an existing substance, chemical substance. Of course, if it's elemental, it's not, but if it's a compound of some kind, it's not going to break that up either. It's still going to be that same formula. So we need to know something about the forces that are holding these things together. So we've got these choices. Let's see, Na2SHF, this one, and this one, and this one. Okay. So what are the forces? What are our choices? Right? What forces can we rely on to hold things in the liquid state? Those are the types of intermolecular forces that we have to overcome. Well, we've got the weakest one, of course, the London dispersion forces. All of them have that. But then if you have a stronger force, then the London dispersion forces just become irrelevant. So the next one up would be polar interactions. Polar-polar or polar ionic sometimes. And then beyond that are the ion-ion interactions. So what do we have to work with here? Lowest boiling point. So we need to know the lowest boiling point. What kind of forces hold this together? Sodium is a metal, sulfur is a non-metal, and they're separated pretty far apart on the periodic table. So you know the bonding there is ionic. And it's going to take a lot of energy to boil that. In fact, that's a solid to start with, so you gotta you gotta make it a liquid first, and then you can boil it. So that one's definitely not going to be the lowest. It should be the highest. HF. Hydrogen fluoride is a covalently bound compound, right? But it has a dipole in that direction, right? So it's going to be a polar-polar interaction with HF and some other HF. In fact, it may even be considered hydrogen bonding, but it's definitely polar. Remember, hydrogen bonding is a special case of polar bonds. How about this one, ammonia? Remember in the first semester, we actually drew the Lewis dot structure for ammonia and used the VSEPR model to say what is its geometry. And it turns out it has that trigonal base with a lone pair up there. So it's going to have a dipole. So the interactions there are polar. How about this one? Dinitrogen. Remember that one? We drew that one in first semester too. It's definitely not polar, right? So what are the possibilities? Well, all you're left with is London dispersion forces. They're the weakest, right? So this one would take a very small amount of energy to boil it. And then, of course, water is actually hydrogen bonding. We know that. So the weakest forces that we have to overcome in all of these groups is this one, right here. In fact, nitrogen boils at minus 195 degrees centigrade. Right? You got to get it colder than that to make a liquid. So just a little bit of heat will make it boil. Okay, I heard somebody ding. Got another attendee. Who am I looking for? Yep. All right. Your gang's all here. All right, that was one. Now this one's not going to erase very well, is it? Let's switch colors. Let's see if this black one works. It erases better. Okay, I want to skip to number 3. When a water molecule forms a hydrogen bond with another water molecule, which atoms are involved in the interaction? Okay, remember the structure of water, like that, there, and it has a couple of lone pairs up here. The dipole for each of the bonds is like that, correct? So the overall dipole is going to make this negative, and each one of these slightly positive. So what kind of interaction can we have here? Well, you can't have interaction between two positives or two negatives, even if they're on different molecules. The negatives and the positives are going to line up in such a way there's your hydrogen bond. Okay, now that we've established that, let's look for the correct answer. A says a hydrogen from one molecule and a hydrogen from the other molecule. No, because they're both positive. How about B? A hydrogen from one molecule and an oxygen from another molecule. That's a good answer, right? Do we have any weird ones down the line, like one of the above or two of the above or none of the above? No. We found the right answer. That's it. B's the answer. That's much better. Black erase is a lot easier. Okay, so let's turn the page. Let's see. Oh, this is one problem on a single page. I know this one. Number 4. We fill up a whole page with drawings, and we really only want to look at Roman numeral 3. That's because in the original set of problems, there was a separate question for each one of them. I only picked out number 3. So you can consider all that other stuff just blue smoke. Which of the following statements are incorrect concerning drawing 3, right? So it's important that you read the question and understand it. Is it in the positive nature or the negative nature? And this one's the negative. which one is incorrect. So we look at our choices. We got 2 of the above are incorrect. All right, so that means we got to look at all of them. E says 2 of the above are incorrect. Okay, so what does A say about, what do we have here first? Roman numeral 3. It looks like we have chlorine and hydrogen bound together, hydrogen chloride. I don't see any water molecules, right? So it's probably a gas. Hydrogen chloride without being dissolved in water is a gas. But what types of interactions do we have here? It looks like we have a dipole set up between hydrogen and chlorine, right? Positive toward the hydrogen. And we're going to have interactions between the negative on one, the positive on the other. Okay, now let's look at the choices. Electrostatic interactions exist between the molecules. Is that true? Yeah, it's definitely true. Just because they're very slight negative positive differences doesn't mean that you have negated electrostatic interactions. You don't have to have a full charge to get an electrostatic attraction. All you need is a slight difference in charge from positive on one and negative on the other to get a bond, to get an attraction. So A is true. B, the molecules find the best compromise between attraction and repulsion. All right. In short, that's true. The molecules, when we say the molecules find the best compromise, in other words, they are looking for the lowest energy state for the combination, right? So they're gonna find the best way to attract. So if they, and randomly they approach one another and it's the wrong end, like positive, positive, or negative, negative, they'll repel until they find an attraction that lowers the overall energy. And when they find that attraction, then they all eventually, they lockstep, you know, at that energy level, at that temperature. If we lower the temperature, then they become more and more and more stable. If we increase the temperature, then we've added some energy that tends to vibrate and break the bonds. So the compromise between attraction and repulsion says that they're looking for the lowest possible energy state, and B is true. These molecules exhibit ionic bonding. Now, it is important whether the charge is slight or full. Is there a complete transfer of electron from one side to the other? No. We don't have an ionic bond here. So C is false. Now we need to look at D and see if it makes E the correct answer, because E says 2 of the above are incorrect. So if D is true, then C is the answer. OCS exhibits this type of interaction. So what do we mean by that? OCS. It's a molecule, and it's bound in that way. Now remember when we said in order to find the dipole nature of a molecule, you need 2 things. First, are the bonds polar? Second, what's the geometry? Well, in this case, you've got a difference between this bond and that bond, right? Oxygen is above sulfur, so it's more electronegative. I'll try to show those relative size. So the dipole for this whole molecule is toward oxygen. And you're going to get a little bit here, maybe represent it like that. So overall, the dipole is going to be that way. Okay? And it doesn't matter what the geometry is. If it happens to be linear, then this one's stronger than that one. If it's nonlinear, right, if it's bent some way, then you're still going to get additive dipoles for this molecule. So polar molecules will behave similarly to this hydrogen chloride scenario. So that makes D true. It does exhibit that type of interaction. So that means E is false and C is your answer. All right. Let's see, what's the next one I chose for our consideration? Let's see. Sure I'm in the right one. Yeah, that one. 6. I want to look at number 6. All right, 6. Scroll down. Here we go. 6. Which best explains the following trend? Well, what's the trend, right? The trend is you've got a series of elements on the left, and notice, how are they arranged? Look at your periodic table. They're all noble gases, right? So if you look at your periodic table, you find that they're listing them from top to bottom. See? Helium, neon, argon, krypton, xenon. And what's happening as you go down and periods get larger? The size of the atom increases. You get bigger atoms, right? Since they're from the same family, you don't have any more valence electrons, outer shell electrons. So the primary difference between or among these noble gases is the size of the atom. So what's happening? As the size of the atom increases, the boiling point increases. So when we say the boiling point increases, that means the strength of attraction between atoms in the liquid phase is stronger as you increase the size of the atom. So if we're going to increase the size of the atom, what does that mean? Well, what forces do we have available? Right? We mentioned some earlier. Ionic? No, these can't be ionic. Right? They're noble gases. They don't form ions. And besides, if they did, there'd be one type of ion and they'd all repel one another. So ionic is out. Are they polar? No, they can't be polar because there's only one of them. Right? There's no competition. So what's left? London dispersion forces. London dispersion forces are more prominent in larger atoms and larger molecules for that matter. Why? Because you have more space for uneven distribution of electron density. And that electron density, even though it's instantaneous, does happen, and it happens more widely, more frequently in larger atoms and larger molecules. So the explanation for this trend is London dispersion forces. A, right? We threw out dipoles, and that includes hydrogen bonding, right? Because there's no hydrogen for sure. And Le Chatelier's principle is just thrown in there to confuse you. Le Chatelier has nothing to do with this. We're not at equilibrium. We're not disturbing an equilibrium. We're describing a physical property of these liquefied noble gases. All right, that was 6. 7 and 8. Yeah, okay, let's see what 7 is. Which of the following compounds has the lowest viscosity? All right, so we want to find one with the lowest viscosity. I better write these up here. Let's see. We have carbon tetrachloride, liquid, nitrogen gas, water, and this one, C3, CH3, excuse me. And then this group 25 times, which just means they're hooked together by carbons. This is organic notation. They're hooked together. The carbons are just a string of carbons, and the hydrogens are off to the side. You got one on the top, one on the bottom, and then there's a bond between two carbons on this side and a bond between two carbons on that side. And it just goes on for 25 units. And then you ended up with the methyl groups on the end. So this molecule actually has 27 carbons. That's probably, yeah, it could be diesel fuel, but it's more, I think it's closer to asphalt. Okay, and then hydrogen chloride gas. Okay, so we're looking for the lowest viscosity. Okay, first of all, what is viscosity? Viscosity is actually a measure of how flowable a liquid is. Higher viscosity means it flows more slowly. It resists movement. So if you take your molasses out of the microwave after you heat it and pour it on your pancakes, you know it flows really easy. And then you put the cap on it, stick it back in the refrigerator. An hour later, you go get it, pull the cap off, turn it upside down, and nothing happens. Its viscosity has increased as the temperature decreases. Okay, so what else influences that flow? Well, low viscosity means that the attractive forces between the molecules is very low, right? There's nothing keeping them from sliding past one another. Let's see, I wrote this before. Here, there we go. So, actually, there's a quick way to answer this question. This is a liquid. This is a gas. That's a gas. Liquids have relative viscosity. You know, we can say this one is the most viscous because it's the largest molecule. And there's several different types of interactions that can slow it down. Water would have a certain viscosity based on its hydrogen bonding. And carbon tetrachloride would be less viscous than water because it's a nonpolar molecule. But gases are always less viscous than liquids because they're farther apart. The forces that hold them together are much weaker. So you can throw out the liquids right off the bat. The least viscous of all of these would be a gas, right? We have two choices here. We have nitrogen and hydrogen chloride, right? So what are the comparisons of forces there? And believe me, you can measure the viscosity of a gas. Here we have dipole-dipole interaction. We just showed it on that drawing. And here we have no dipole. The forces are weakest here. So this one would be the least viscous. Nitrogen gas. Oh, and that's B for this particular problem. Okay, let's look at number 8. Oops, there. All right, 8. When a nonpolar liquid displays a convex meniscus, which of the following explains this behavior? All right, let's read it backwards. What's a meniscus? Well, to have a meniscus, you need a liquid in a tube, a container of some kind. So if we have a tube and we got a meniscus, whoops, what is it? Convex. Convex means bowed up like that. Okay? And your liquid's down here. And I guess you have some kind of a container. What does that mean? Well, think back to our discussion of competing attractive forces. One of them is called adhesive. Oops, can't spell this morning. And the other is cohesive. They're opposite actually they're converse, I would say. Cohesive forces are those that hold the liquid together, that the liquid molecules attract one another. That's cohesive. Adhesive are forces that tend to attract the liquid to its container walls. Right? So these two forces are in competition, and the meniscus, it depends on which one wins. If it's a convex meniscus, then the internal attractive forces win. They're pulling that away from the walls. That's why it's like that. So the cohesive wins. If it were the other way around, like water in a glass tube, be the other way. And the adhesive forces would win. So let's look at our choices. This is a nonpolar liquid. Which of the following explains this behavior? How about A? It has a low surface tension and therefore clings to the glass. Well, if that were true, you would expect this, because it would be more attracted to the glass because of low surface tension, right? That can't be. Well, actually, think of what water. Surface tension of water is what we would consider high, right? Otherwise, you wouldn't be able to take a needle and set it on a calm dish of water and turn it loose, and it hangs there, right? The surface tension of water is very high, and it gives you a concave meniscus. So A is false on 2 counts. B, the cohesive forces are stronger than the adhesive forces. That's the good one. And since it's true, and E says none of these, then, you know, if you're in a hurry on a test, you stop there. You got the answer. If we look down at C, the adhesive forces to the glass are stronger than cohesive. It can't be. You can't have B and C both be true. It's either one or the other. And the liquid's viscosity is low. If the liquid's viscosity were low, then it would have very weak intermolecular forces holding it together, right? And in that case, the cohesive forces would be low, and more than likely the adhesive forces would win, and you'd have a concave meniscus also. So B is the answer to that one. Let's see, did I erase that prematurely? Let me see. Yeah, no, we haven't finished the easy yet. Okay, how about number 9? Which substance can be described as cations bonded together by mobile electrons? Think back to the end of the chapter, I think it was. We were talking about various models that were proposed for the way metals bond with each other. And one of the first models was this electron C model, right? So it has its advantages because it's really simple. You know, it doesn't involve any math. We found that the more accurate and useful model for metal bonding is derived from the molecular bonding model. But in this case, we're still talking about cations, the metal cations, because all metals prefer cations to anions when they ionize. So they tend to, their valence electrons tend to be fairly easy moving about. And they move from one energy level to the other and attract whatever positive is close to them. So what you need is to find the metal in all of these answers. And that happens to be A. This is the only metal, silver, right? Sulfur's a nonmetal, krypton's a noble gas. KCl has a metal in it, but the ions are not free electrons. The electrons are transferred to chlorine. So you have the chloride ion and you have the potassium ion. So you don't have mobile electrons. They're bound to the chlorine. And HCl is a covalent compound that's polar. Right? So you can't claim that the electrons are mobile there either, even less so than KCl. All right, so 9 would be A, silver. The only metal in that, the only free metal in that group. Okay, how about, 10? Which of the following statements about steel is false? So let's see, what are our choices? E says all of these are true. Okay, so it's possible. You know, if all of them are true, then actually none of them are false. So let's look at the possibilities. Steel contains carbon atoms in the holes of its iron crystals. Remember when we were talking about alloys? Sometimes you mix metal and metal, and sometimes you mix metals and nonmetals. And you have two types of alloys. You have the substitutional, or you have the interstitial. Okay, substitutional is where you would remove an iron and replace it with something else in the crystal matrix. Interstitial is where the irons stay put and you put things into the holes, the gaps between the iron atoms in the crystal. Steel is one of those, where you have the irons like this, and you fit a carbon right there, right there, right there. Okay. Steel is an interstitial alloy in its original form, just iron and carbon. Now, when you start adding other things, then you get a combination of the two. For instance, stainless steel. Stainless steel originally had 35% chromium. Now you can get stainless steel with about 13%. But you still need the carbon. So you got a combination of interstitial with the carbon and substitutional with the chromium. And they had various other. So the interstitial atom has to be small enough to fit in the holes. And of course, if you look where carbon is located, it's way up here toward the top, it's going to be a small atom compared to iron, which is way down here. Okay, so let's see, which is false. That one, A is true. The presence of carbon-iron bonds in the alloy makes steel harder and stronger than pure iron. That's also true. What the carbon does is while it's in those little holes, it forms bonds with its neighbors and keeps the iron from sliding past itself. If it's pure iron, you can scratch it with your thumbnails, so soft. But if you stick carbon in the middle, then the carbon tends to lock those iron crystals in place. Can't move them easily. And that's why steel is harder than pure iron. Pure iron is relatively soft and ductile because it lacks directional bonding. That's true. I just said it. It has that sea of electrons and it's bound in multiple different directions, if you want to use that model. And D, the amount of carbon directly affects the properties of steel. And that's definitely true. If you have upwards of 2 to 5% carbon, you actually don't have steel. That's too much carbon. You have cast iron, for instance. Steel, you need 0.5% or less. And actually, 0.5% carbon is considered high carbon steel. Less than that, like 0.2 or 0.1% would be lower carbon steel. And they have their applications. And the different properties based solely upon the percentage of carbon. Okay, so all of them are true. 10 is E. All right, 11. All right. Okay, just when we run out of time, I'm going to keep talking. All right, so don't worry about it. It's going to be recorded. 11. Which of the following statements is true about p-type silicon? Now, what do we mean by that? Little p, that's not phosphorus. That's little p that references positive charge. All right, so p-type silicon, you have silicon, pure silicon, something like that, you know. And it's a non-metal, and it's a non-conductor, right? It's actually a metalloid. Sometimes it acts like a metal, and sometimes it acts like a non-metal. But pure silicon is relatively free from conductive properties. It doesn't conduct heat or electricity very well. So with a p-type silicon, what you do is silicon has 4 valence electrons each. Right, 4 electrons. Right. So there's really no preference. There's really no mobility of electrons. They're bound pretty tightly to silicon. It's in the carbon family. But if you substitute something in there that has less than 4 valence electrons, then you've created a hole in there, absence of 1 electron, that is represented by a positive charge. But it's really not a charge, it's just the absence of an electron, but it allows more easily the movement of electrons in that matrix. So which ones have 1 less electron than silicon? Well, if you look to the left, that's where you would go. You add valence electrons to the right and you subtract them from the left. So let's say silicon, if you put aluminum in there, or gallium, or boron, right? They're that family to the left. Boron, aluminum, gallium would be good choices. Boron, aluminum, gallium. Those are all 3 electrons in their valence shells. And remember, we're aiming for a p-type. So if they come from the other side, 1 extra electron, we have the n-type semiconductor. So let's see what our choices are. Which of the following are true? We've got choices. All are true, none are true. So we got to look at all of them. It's produced by doping silicon with phosphorus or arsenic. So where are phosphorus and arsenic relative to silicon? They're to the right, right? So they make n-types. So A is false. So D can't be true. Can't have all of them true if one of them is false. So now that throws out D, and we just need to look at B and C to see if E could be true. None is true. So we got 1 false one. How about B? Protons are the mobile charge carriers. What's wrong with that statement? If a proton goes anywhere except right here, you don't have silicon anymore. You can't move protons and expect to retain silicon. If you move a proton, then you're going to get aluminum, right? That doesn't happen. Only electrons are mobile. So with a p-type, if we put, say, boron in here with 3 electrons, we represent that as a hole, an absence of an electron. And we say the hole moves, right? That's a conceptual trick to help us visualize what's happening. What actually happens is the electron moves this way, and the hole now is over here. Okay? So protons can't move. C, it does not conduct electricity as well as pure silicon. Well, fact is, it does conduct electricity better than silicon. I mean, it's not a full conductor like a copper wire would be. You don't have mobile electrons. They are restrained. That's why they call them semiconductors. They're kind of in between insulators and conductors in the middle, which gives you actually more control over where the charges go. And you can form logic gates, as they call them, in the semiconductor industry. And you just stack those logic gates together and you get memory modules. That's another story. So all of these statements, A through C, are false, which makes E true. None is true. Okay, let's see. 12, did I pick? No, not 12, 14. Let's look at 14. Solid crystal of sodium chloride. I may have asked you this before. You ever spill salt on a table and then pull out a magnifying glass and look at the crystals? What shape are they? They're always cubes. All right, regular cubes. Well, that doesn't answer this question. Sodium chloride is a solid crystal, which means what? It's an array of positive and negative charges. So how many chlorines surround that sodium? In this plane, there are 4, but there's a plane behind it and a plane on this side. So actually 6 chlorides around the sodium. Similarly, you've got 6 around the chloride. So you could say that the formula for sodium chloride is N6Cl6, but we go with empirical. So the simplest whole number ratio is 1:1. But that still, this says that they're locked in that crystal structure. And when you have to conduct electricity or conduct heat, you need mobile ions. If these things are locked in place, they can't move. It's a solid, right? So the only way that they could transfer energy is by wholesale movement of the ions. And that goes for transfer of heat or transfer of electricity. Also, they're strongly locked in place with ionic bonds. So let's see what that means in terms of our potential answers. A solid crystal of sodium chloride is soft. Is that true? No, it's hard. It's very hard. So that means A, C, and E can't be true. They're out. Doesn't matter what the rest of the answer is.
So B or D will be the answer. So hard, that's true. High melting, yes. That's a lot of energy to overcome. I mean, they're very stable. They like being positive, negative together. And it takes a lot of energy to pull them apart. So they're both high melting. So we're still B or D. B says good electrical conductor and D says poor electrical conductor, right? Based on that previous description, they cannot be a good electrical conductor because the ions are not mobile. They're locked in place. So D has to be the answer. So what are the other options? If we want sodium chloride to conduct electricity, we got to either liquefy it to free up these ions and let them move, or put it in solution. Then the ions can move, like sodium chloride. Sodium chloride solution is an extremely good conductor of electricity. Water is not. Water doesn't have any mobile ions unless you get the voltage really high, like 10,000 volts or something like that. Then you can start forming ions, and then you can get water to conduct. Okay, so D is the answer for 14. Let's see, what's next? 15. Which of the following has the highest melting temperature? All right, so continuing with our previous discussion, which one would have the highest melting temperature? The one that has the most strongly bound parts. What is that, 15? Well, I'm going to work from the document. So which ones, well, let's find out which ones have the weakest interaction. Well, the ones that are not polar, for instance, like S8 is a symmetrical molecule of 8 sulfurs. P4, symmetrical, actually it's tetrahedral form. I'm not sure what S8 is. If it were 6, it'd be octahedral. S8, I don't know what that one is. But those have very low melting points. CO2 has an even lower melting point. It's a non-polar covalent compound. Water has its melting point 0 degrees Celsius, right? So it's higher than the rest of them, except for this one, this ionic compound, magnesium fluoride. Remember what our discussion was about what determines the strength of the ion-ion bond, ionic bond. 2 things, the size of the charge and the distance between them. So if we get a large charge, like magnesium is a 2+, fluorine is a 1-, and then if you get them close together, magnesium is a very small ion, and fluorine is relatively small anion. So you can get them close together, and the bond energy here is very high. Takes a lot to break it apart. That's why D is the answer. Okay, 16. Which of these statements is false? Diamond is a covalent crystal. Is that true? Yep. In fact, if your diamond has no flaws in it, the diamond is a single molecule, a covalently bound molecule. B, the size of the unit cell of lithium and cesium is the same. Could that possibly be? Lithium and cesium are in the same family, right? They're both alkali metals. What's the difference? Lithium is very small, cesium is very large. So the size of the unit cell can't possibly be the same. Lithium's going to be able to get closer together to its neighbors. Cesium is going to be pushed farther apart. So B is false. Okay, E can't be true because we found a false one. How about C? Molecular crystals usually have a low melting point. That's true. The internal bonding for a molecule is covalent. And the influence on melting, what holds the solid together? Intermolecular forces of some kind, right? They can't be ionic, right? So they either have to be polar or London dispersion. And they're a lot lower. They give you a lower melting point. A lot less energy is required to break those bonds. Metallic crystals are usually good electrical conductors. Metallic crystals, that is when there's just a metal and it's sea of electrons, they are good conductors. That's characteristic of metals, among other things. They'll also conduct heat very well too. So B has to be the answer for 16. How about 17? How would you expect the melting point of carbon tetrachloride to compare with that of sodium chloride? Well, before we look at the answers, carbon tetrachloride is a polar covalent compound. It's going to have a very low melting point. And sodium chloride is an ionic solid. It's going to have a very high melting point. What we need to do is find the answer that addresses that correctly. And if it's got any theoretical backing, that has to match also. So what about A? It should be lower because, so this melting point of carbon tetrachloride should be lower than sodium chloride because sodium chloride forms an extended ionic crystal lattice, whereas carbon tetrachloride is covalently bound small molecule. That's as true as it gets. And if you don't have any others down here that augment the potential answer, then you found your answer. And in the interest of time, I'm going to move on. 19. At normal atmospheric pressure, 1 atmosphere, and a temperature of 0 degrees Celsius, which phase or phases of water can exist? Remember that drawing? Let's see, we're up to 19 now, sorry. Remember that phase change drawing where you have temperature here and progress here. So if you start off at, say, minus 20 C, and then you go up to 0, and then you go up to 100, like that. And this is water. So if you start off below 0, the heat that you're adding to the ice is just warming it up. You're making the molecules vibrate. So as you progress, you increase the temperature as you add heat. When you get to 0 degrees, now you're adding energy to melt. And the temperature stays the same. So down here, you have nothing but solid. Here, you have solid and liquid, both at the same time. Then once you get all liquid, you can start increasing the temperature again. Right? You get to 100 degrees. Here, you have only liquid, and you're heating the liquid up. And once you get to this point, you're making gas. Liquid and gas together, boiling water. Once you get all the liquid gone, now you're heating up the gas. And that's industrially useful as superheated steam. It's a very efficient way to transfer heat from one place to the other inside a processing plant of whatever kind. Okay, so to answer this question, we say at 0 degrees, right, which phases of water can exist? Liquid and solid both at the same time. That's why A, ice and water can exist at the same time at 0 degrees centigrade. And that's why I said in the past, if you've got distilled water and ice made from distilled water, and you have both of them in the vessel, you say you have water and you add ice to it, and you add enough ice so that now you have both water and ice together, you're guaranteed 0 degrees Celsius. And we often use that in the lab to calibrate our thermometers. That's one stable temperature. And in fact, that's the way Celsius devised the temperature scale. He put those two together and he set his 0 point wherever that was in ice water. Okay. Let's see. We're going, yeah, 20. Okay. So we're going to look at 20. Here. Let me keep track of my time here. We're good till noon. Oh, good. I got 2 more hours. We might get finished after all, if we're lucky. Which of the following processes here must exist in equilibrium with the evaporation process when a measurement of vapor pressure is made? All right, so let's look at how we're going to measure vapor pressure. You need a vessel, and you got to have a lid on it, a sealed lid, and then you have a liquid and the vapor. So liquid down here, vapor up there. So when you first put this liquid in the container and seal it, what happens? Well, you get, it's like a one-way street. It's all evaporation, right? Until you get enough of the liquid molecules in the gas phase so that they start returning. And then they return, and that's called condensation. Okay? So the process that exists in equilibrium with evaporation is condensation. Right? So that E is the answer to that one. But I want to expand on that thought because it's useful to think of phase transitions in kind of a triangle. We put the solid up here. Yeah, I need to, let me see if brown works. I need a solid up here. And then I need a gas over here. And a liquid over here. And you have processes that occur when these phases are transitioning from one to the other. Right? So if we say we just did liquid to gas. So if it's going this way, it's evaporation. And if it's going this way, it's condensation. Okay? Between liquid and solid, you get, let's see, outside. If it's going this way, liquid to solid, you've got, sometimes they call it freezing. But the proper chemical term is called fusion. So when you see an expression, the delta H or the heat of fusion, they're talking about liquid to solid transition. Coming back the other way is melting. All right, so we have one other possibility, solid to gas. If we're going, let's see, this way, if we're going solid to gas, we're called sublimation. okay? Like dry ice on a hot pavement. It doesn't produce any liquid. It goes straight from solid to gas, carbon dioxide. Going back the other way, we call gas to solid, we call deposition. Okay, so those are descriptive terms for each of these processes. All right, so let's look at 21 and 22 together. They use, I think, maybe. We'll look at 21, definitely. Okay, 21. You're given the following boiling point data. Which one of the liquids would you expect to have the highest vapor pressure at room temperature? Okay, so the question is vapor pressure at room temperature, right? So if we hold the temperature constant at room temperature, whatever, 25 degrees is standard. Celsius temperature. So what contributes to vapor pressure? What are the forces holding the molecules together in the liquid phase? If they're weak, the vapor pressure goes up. So how do we know what those forces are? Well, the boiling point is a good indicator. Higher boiling point means stronger forces holding them together. So if the stronger forces are at play, then the vapor pressure will be low. So what does that mean? That means low boiling point, high vapor pressure. Right? That's the one inverse relationship we talked about in that particular chapter. If the intermolecular forces increase, all other measurements or physical properties increase. But for vapor pressure, the intermolecular forces have to be decreased for the vapor pressure to increase. So we're looking for a low boiling point, not relative to room temperature, but relative to what are the forces holding the molecules together. So we're looking for the lowest boiling point to give us the highest vapor pressure. And that turns out to be D, diethyl ether, 34.5 degrees Celsius. So you have a gloved hand and you pour some diethyl ether in it, and before too long, it's gone, right? Because what's your body temperature? In Celsius, right? 98.6 Fahrenheit. 37 degrees Celsius is normal body temperature. So if your boiling point is 34.5, it's going to boil off pretty fast. And you'll smell it too. And you don't want to light a match either, because it's flammable. Okay, 22. Which of the following decreases as the strength of the attractive intermolecular forces increase? All right, we've already answered that one. The only one where the property increases in its value, the other way around, decreases as the strength of the intermolecular forces increase, is the vapor pressure. So the vapor pressure of the liquid increases as you decrease the forces holding the molecules together. That's why I had those two. I couldn't figure out why I bracketed them together. It's the same explanation for a different problem. Okay, 23. In which of the following processes will energy be evolved as heat? Right. So think back to our study of enthalpy. or heats of reaction. When we talk about heat transfer, it's always relative to the system. So, we're looking for energy to be evolved. That is, heat's going this way. And that means it's leaving the system, which means it's negative. If it's going this way, heat is positive. Okay? So we want something that will give up heat. Now, why would a system give up energy? Most of the time, energy is being given up when the system itself is becoming more stable. Stability evolves heat. So, if your state of the system is liquid and then it becomes solid, the solid means that the molecules are closer together, well, usually, but they're more stable, except for water, right? That's the outlier. But usually, the stability of the system is increasing as it goes from liquid to solid, and it gives up heat, right? So the phase transition from gas to liquid to solid should evolve heat. So let's see if any of these in here satisfy. If we're going from sublimation, solid to gas, we have to add heat to the system to make it go from solid to gas. It takes more energy. So that can't be it. Crystallization. What happens in crystallization? Well, you have separate molecules or ions, and they come together into a solid. They may be in solution, or they may be a process of deposition, or go from a gas to a solid. But the formation of the crystal is more stable, so it gives up heat. And that answers your question, right? E can't be it, none of these, because we found one that's true. Vaporization absorbs heat, melting absorbs heat. Crystallization is the only one that gives up heat in that process. All right, let's see. No, we're going to skip that one. 25. So we have a phase diagram here. Notice it's identified for you things, pressures on the y-axis, temperatures on the x-axis. And with those arrangements, we draw phase lines. In other words, right along this line here, if you can see my cursor moving, I'll wiggle it some. Right along this line is the phase between solid and gas. So anywhere along that line, at that temperature and pressure, you have both solid and gas together. Similarly, if you follow this line, at that temperature and pressure, anywhere along that line, you have solid and liquid together. So if this were water, which it's not, of course, that should be obvious, then at 1 atmosphere, this temperature would be 0 degrees to have solid and liquid together. But what's different about the water phase diagram? The slope of this line for water is negative. It's not positive. It goes back the other direction. And similarly, liquid and gas along this phase line. Okay, what's the question? The correct statement we're looking for. So let's see. What's statement? Let's see, we're on 25. Statement A says, the diagram is qualitatively correct for water. That's wrong because of the slope of that line. The liquid-solid slope phase line for water slopes negative. Goes back the other way. That can't be it. E, let's look at E says none of the above statements is correct. So that means if we find one correct one, we can stop. B, the diagram shows that the melting point of the solid, where's the melting point? It's the phase line between solid and liquid, right? Melting along that line. The melting point, which will change, will it not? Right? It's not a vertical line, it's sloped. So the melting point, this temperature, changes as the pressure goes up. In fact, it increases as the pressure increases. So increase the pressure, we get a higher temperature. Look where it goes. Let's look at the intersection on that line. Temperature increases as we increase the pressure. And that's exactly what B says. So B is true. We can look at C. The diagram shows the triple point above 1 atmosphere. Where is the triple point? It's the one point on that phase diagram where solid, liquid, and gas exist at the same time. So at this temperature and that pressure, all three phases exist at the same time. Is that anywhere near 1 atmosphere? No, 1 atmosphere is way up here. So C is false. How about D? The diagram could represent the phase diagram of CO2, carbon dioxide. Well, let's see. Could it? If we were at 1 atmosphere, we stayed at 1 atmosphere, and we let the temperature of the solid carbon dioxide increase, right? It's that brick of solid, of dry ice sitting on the pavement in the hot sun, 1 atmosphere pressure, right? We're increasing the temperature, but the pressure is not changing. So we follow that 1 atmosphere along here as the temperature increases, and we go from solid to liquid, not solid to gas. So this cannot be carbon dioxide, right? That 1 atmosphere line would have to be way down here where we could follow solid directly into gas. Okay, that's why D is false. 26, we get another phase diagram. Okay, so we've got solid here, liquid here, and gas there. And now the temperature scale is in Kelvin, and pressure is in atmospheres. Okay, so let's see. They're saying this is a phase diagram for a compound Q. Oh, 26. Let's see, do I need to sketch that one? Hopefully I can do that in the interest of time. Let's see if we can do it on the page. You want to purify a sample of Q that was collected at P equals 1 atmosphere and T equals 100 K. Maybe I can annotate. I wonder if I could do that. Annotate. So let's see, I want, what do I want to draw? Okay, let me mark position here. Collected at 1 atmosphere and 100 K, so it's about right there. Yeah. Let's try it again, right here. Right there, okay? So we've collected Q at 1 atmosphere and 100 K. So it's pretty cold, actually, right? 0 degrees Celsius is 273 degrees Kelvin, way out here. So it was very cold, but it was at 1 atmosphere. And we want to purify it. So we want to purify it by sublimation, which means what? We've got to cross this line right here. Right? From solid to gas. So how would you do that? Well, you could stay at that temperature, you know, and just decrease the pressure at that temperature. and you would sublimate it. Or you could drop the pressure down here and then go this way, increasing the temperature. All right, so what are our choices though? What if we increase the pressure to 1.5 atmospheres up here, and then increase temperature to 300 K? So if we go up here and cross over like that, you're going from solid to liquid. That's not sublimation. How about, let me change my annotation to a line. Where is it? Draw, line, here we go. So if we go, what's the, A is false. B, increase temperature to 300 K. So if we go 300 K from here to here, like that, we'll still go straight through liquid before we get to gas. That can't work either. So B's false. How about C? Lower the pressure to 1/2 an atmosphere. So take it down here, right there, and then increase temperature to 200 K. So we go from there and we go over here like this. That'll do it. That will give you sublimation of your sample. And the idea is that when you sublime the sample, the impurities that are in the sample will not sublime, right? The forces holding the impurities together are stronger than the forces holding the compound Q together. And that is how you separate them. Use sublimation, because you leave the solids behind. Okay, so we found our answer. It's C. Let me see, I need to go back to, let's see, here we go. There we go. Oh, I need to erase that, or it's gonna hang around. There we go. All right. Go back to my mouse. Okay, so that was 26. Or was that 27? I forgot to write 27 up there, didn't I? No, there's 27. Let's see, are we going to look at that one? No, we're going to skip 27, 28, and go to 29. All right. 29. Given this phase diagram, 29, which of the following statements is false? Well, let's see. The solid has a higher density than the liquid. All right, this is kind of, you sort of have to dig into your past, your knowledge of phase diagrams, and recognize that this phase diagram looks more like water than others. Most of the time, the slope on this line is, let's see, most of the time the slope is positive, like this, right? But for water, the slope is negative. And what do we know about water? We know that the solid is a lower density than the liquid. Okay? So that makes it look like water and makes this statement false. But that may not be the whole story. So we need to look at the others also. A, let's hold A in reserve. A could be the answer. And don't look at the answer. Pay no attention to that man behind the curtain. B, at some constant temperature, the gaseous substance can be compressed into a solid and then into a liquid. okay, at some constant temperature. So we have to hold the temperature constant somewhere and go from gas to solid to liquid. So if we decrease the temperature down to here, and then we go from gas, we go through solid and then into liquid, just like water. That's true. Okay? So B is true. C, when phase A over here is compressed at constant temperature at point X. So from point X we're starting and we're compressing it at that temperature. We're not changing the temperature. What happens when you compress it? Well, it goes like this, right? So what does that mean? No change is observed? It depends on what you mean by change. Well, we're talking about phases here, right? So you're looking for a change of phase. And usually, whenever you change phase, you do see a difference, right? There's a difference. Usually, there's a difference in refractive index. That is how it bends light. And you can see that when you go from one phase to the next. But when you increase the pressure at this temperature, what region are you in? What is that point right there? That is the critical point. At that temperature and that pressure, anything beyond there, out in this region, out in that region over here, and it's kind of nondescript actually. Anything out there, you can't tell the difference between gas and liquid. So if you start at a gas and you move into what you would expect to be liquid, you can't see a difference, right? So C is true. No change is observed. Okay, so D, when heated at 1 atmosphere, this substance will first melt, then boil. So if we're at 1 atmosphere and follow the line 1 atmosphere and we heat it, we go like this, like that, and like that. Let's see, let me make that horizontal. There we go. It will go through from solid to liquid to gas. That's true. So there's only one false statement in there, and that's A. Okay, that was 29. Now we're into the moderate section. Right. The reason I have to do that is because I start renumbering with the sections. So moderate, now we start with 1 with the moderate section. So number 1 in the moderate section, hold on a second, let me get my cursor back, my mouse. Okay. Here we go. Which of the following is correct order of boiling points for these? Okay. So we got to put them in order, and it looks like all our choices are increasing, right? Based on that caret. So we put them in low to high boiling point. So how do you do that? Well, you look at the, use this. You look at your choices, and the way I do it, when you got to put something in order, I like to nail down the ends, right? What's the highest boiling point? What's the lowest boiling point in this case? And then fill in the middle with the others. So what's the highest boiling point that you would expect here? Well, the ionic compound. Potassium nitrate is ionic. The rest of them are not, right? So this would be the first one. That would be, actually that would be the end, excuse me. That would be the last one, the highest boiling point. What's the lowest boiling point? The one with the weakest intermolecular forces, right? This is nonpolar, but so is neon. And neon's a lot smaller. So the chances for London dispersion forces for neon are to be a lot smaller than for ethane, which is C2H6. So neon would be at the other end. Right? So we got our ends nailed down. So let's look at our choices, right? Test-taking technique. Which one has the neon on the lowest end? A and D. Okay. How about KNO3 on the highest end? KNO3, KNO3. So the rest of them are out, right? Because this neon doesn't have KNO3 at the highest end, right? So it can only be A or D. So now we need to look at these two in the middle. Which one would have the lowest boiling point of these two? Look at the possibilities. C2H6 is a hydrocarbon. It's a non-polar compound. If you didn't know that, look at this one. It's got the possibility for hydrogen bonding, right? That one doesn't. So this one's going to be stronger. Even if that one were polar, this one would be stronger in polarity than this one. So the farthest one to the right is going to be this one, and then this one will be to the left of it, right? So let's see which one of these fits. A puts, oh, that one's on the wrong side. It needs to be this one right here, over there. So that one fits with this one, and this one is higher boiling point. So D has to be the answer there. Let's see, 1, 2. Let's see, I may not have to put these on the board if I can keep annotating like this until I have to work a math problem, and they're coming. So let me see here, I need my mouse back. Okay, 2. Which of the following statements is or are false? This one's a little difficult because it requires that you remember, first of all, whether or not hexagonal closest packing is also associated with ABA layered structure. And in fact, it is. That's true. Remember when we were talking about those crystal structures that the closest packing model versus, well, actually, closest packing and the unit cell and the layering ABA versus ABC A, they were all, well, now I can't say that opposite sides of the same coin because my coin's got 3 sides on it now, but they're all related. And hexagonal closest packing is also expressed as ABA layering. So 1 is true. We need to find false. How about a body-centered cubic unit cell has 4 atoms per unit cell? So I am going to have to draw this one up here. A body-centered cubic cell. So we got a cube. That's in the background. Well, this is in the background too. Anyway, so we got a cubic cell. We've got atoms or ions occupying those positions. And now we need one right in the middle. Body-centered cubic. How many atoms does that represent for that cell? Well, we know that that one belongs to this cell. How much of this one belongs to that cell? Well, it depends on how many other cells are claiming parts of it, right? So you've got, it's claiming a part here, and then there's a part out here, and there's a part over here, there's a part up here, there's a part over there, part over there. Turns out that that cell can only claim 1/8 of that cell, of that atom or ion. But how many do you have? 2, 4, 6, 8. So 8 times an eighth is 1. And there are 2 atoms, if we're using atoms only, there are 2 atoms to that cell. So 2 says 4 atoms. That's wrong. Can't be. Which one actually has 4 atoms? Face-centered cubes have 4. Okay, so 2 is true. So it could be B, or it could be C, or it could be E. We need to look at 3 and 4. For unit cells having the same edge length, okay, so we got 2 cells. They both have the same length of edge. So what does that mean? That means they're the same size cube, exactly the same volume for their unit cells. A simple cubic structure would have a smaller density than a body-centered cube. Okay, what do we mean for density? Mass per unit volume. So if you're comparing densities and volumes the same, the only thing that can change the density is the mass of the unit cell, right? So if it's simple cubic, you've only got 1 atom per unit cell. If it's body-centered, you have 2 atoms. So a simple cubic would have a smaller density because that is smaller for the simple cube than it is for the body-centered cube. So 3 is true, right? Well, that means that C or E can't be true because 3 is true and B is false, right? So you can stop there if you want. And in the interest of time, I think I will. All right, skip down to 4. Okay, now we're going to have to do some ciphering, as Jethro would say. You know, Jethro Bodine, I think his last name was. Okay, assume that you have 12,500 joules of energy, and you can add it to 2 moles, which is 36 grams, of water as an ice sample at 0 degrees. Okay, so let's look at that. I'm going to draw a smaller diagram over here. Right. So we've got our phase transitions here. Right. So down here we have nothing but solid. Here we have solid, liquid. Here we have liquid. Here we have liquid, gas, and here we have gas only. So we're starting out at 0 degrees. So for water, it's right here. Right at the very beginning of that flat line. Nothing but solid. So any energy we add to that ice is going to start to melt it. It's not going to change its temperature, it's just melting it. All right, so we add that energy to 2 moles. So we have N equals 2 moles, or mass equals 32 grams. Same thing for water. And we have energy, total energy is 12,500 joules. Right, so we're going to use that up, energy, use it up as we transition through the phases. The molar heat of fusion is 6.02 kilojoules per mole. And that's for ice because it's the preceding statement said ice sample. And the molar heat of fusion means melting. Right? So that's how much energy per mole it takes to melt ice, 6.02 kilojoules per mole. So how many joules is a kilojoule? Right, times 1,000. 6,020 joules per mole. And we've got 2 moles. Yeah, 6,020 joules per mole equals what? 12,040 joules. We use that much up just to melt the ice and make liquid. So now we have liquid. All the solid's gone. And what do we got left? Let's see, minus 12,040 joules. 0, 6, 4. 460 joules left over. Now what we're doing is we're heating up the liquid. So if we use up all of this energy and we're still in the liquid phase, then that answers our question. If we have an excess, we don't use it all up, and we make it to the gas-liquid transition, then we have gas and liquid together. So let's see, what's the next step? The specific heat of liquid water is 4.18 joules per gram per degree C. All right, so remember the formula. Q equals specific heat times mass times change in temperature. And the change in temperature is final temperature minus initial temperature. Okay, so Q is 460. That's what we have to play with. Well, actually, let's not do that. That's what we have to play with. How much is it actually going to take? That's the question. So Q would be equal to specific heat 4.18, I think. Yeah, 4.18. I'm going to leave the units out because of space. Mass is 32 grams. What's the final temperature? We don't know. Or do we know? No, we don't. We don't know what the final temperature is. We know what the initial temperature is. It's 0 degrees. We can do this 2 ways. We can plug in the final temperature at 100 degrees. So by the time it gets to 100 degrees, is that value greater than this value? If it's greater than this value, then we don't have enough energy to get there. Or we could plug in 460 and say, what's the final temperature? If we use all this up and say the final temperature is between 0 and 100, that's probably the better way to do it. So let's substitute this 460. There we go. Now it's solved. That's 0, right? So all we have to do is say, divide this by that, and this, and by these 2 numbers, those 2 divided into 460, and see what the temperature is. It'll take me just a second. Pull out the calculator and say 460 divided by 4.18 and divided by 32, which is 3.4 degrees. That's a far cry from 100 degrees, isn't it? You're still only liquid, right? Only water sees the answer. See, am I still? Yeah, I'm still in frame. Okay, that was 4. Let's see, skip 5. Now we're getting to difficult. Difficult. Let's see. Let's do number 1. This is going to take some ciphering also. Let's move it, move it, move it. There we go, 1. Okay. A crystal was analyzed with X-rays, having a wavelength of 2.33 angstroms. The angle of the first order diffraction, where n equals 1, was 19.2 degrees. What will be the angle for the second order diffraction? All right. What are we talking about here? We're talking about the Bragg equation, which relates the angle, the order angle, to the wavelength and the distance between the crystals within the layers of a crystal. Right? So you're going to need the Bragg equation, and it's right there in your useful information, right, which will be available on the exam. By the way, since this exam is taken using Lockdown Browser, on the first exam, it would be a good idea to go in with your normal browser and go to the exam 1 folder and find the useful information document that I have in that folder and print a copy, or whatever there happens to be there in that. I think I put it all in one document. So you just print that document and you can use that during the test. Then go into your Lockdown browser and Respondus and go through the rigmarole and picture your ID and get your face recognized and all that stuff. And then when it finally lets you into the exam, the folder where the exam is, then access that useful information. And the reason I want you to print it out first on this exam is so that you'll have it there in case I'm wrong, and in case Lockdown Browser prevents you from opening any other documents. That could be possible. So this is kind of a test to see if the useful information is going to be available inside Lockdown Browser. If it's not, then every time you take an exam, go print it out first, and then start the Lockdown Browser. Okay, back to the useful information. So the Bragg equation says that order, n times the wavelength, is equal to, where is it? Well, I had it just a second ago. There it is. 2 times the distance between the crystal layers times the sine of the angle of incidence of the light beam. In this case, it's X-rays. Now, one other thing that you may need to know. What's an angstrom? 1 angstrom is 10 to the minus 10th meters. Okay? Or 10 to the minus 8 centimeters. Okay. So now let's go back and look at the information that's given. The wavelength of the X-rays does not change. It's the same for both. So the wavelength is equal to 2.33 angstroms. All right. The angle of the first order, n equals 1. Let's see, when n equals 1, the theta, first order, equals 19.2 degrees. Okay? When n equals 2, that's the question. Right. What's the angle for the second order? All right, we're going to use a little algebra here. It's not going to be too complex. But we're going to have 2 equations. One for this one and one for that one. So if we solve for this equation, we know that n equals 1, and the wavelength is 2.33. Then we have 2, and d, the distance between the crystal, we haven't solved it yet, but sine theta, and theta is 19.2. So it's sine 19.2 degrees. Okay? So there's one equation. How about the second equation? The second equation says n is 2. Wavelength is the same. 2 is a constant. D is the same. And the sine of theta 2. Okay. So we have two equations, and how are they related? They're related by the crystal. The crystal hasn't changed, right? You can just leave it in the machine. It's the same one. It's got the same distance here between the layers for each one. So if we were to solve one of them for D and take that equivalence and plug it in D for the other one, then we should be able to solve for the unknown. Right? So if we solve this one for D, that actually it doesn't matter. You know, pick one. We can solve this one for D and plug it into that one. Okay. Right. Last time I worked this problem, I did it that way. Now I'm going to do it this way, just to be sure it works. So let's solve this one for D and plug that equivalence into that D. So what would this D be equal to? Well, let's see. If D's on this side, then everything else goes into the denominator on that side. So 2.33, and then underneath is 2. Let's see, and sine 19.2 degrees. Okay, so now this is equal to D. We can plug it in right here. So I'm going to come over here a little bit. 2 times 2.33 equals 2. And then what is D equal to? D is equal to 2.33 divided by 2 times the sine of 19.2 degrees. Right? And that times the sine of that one. Okay? Now what we have to do is reduce the equation so that the sine of theta is equal to some number, and then we can solve for theta. So what do we have? Well, let's see. We got 2 in the numerator on both sides here, right? 2, 2. That's gone. We got 2.33 on both sides in the numerator, so that one's gone. So this one is in the denominator, 2 times sine 19.2. 2 times the sine of 19.2 degrees equals sine theta, correct? So what is this number equal to? 2 times the sine of 19.2. Sine 19.2. You have to learn your calculator. Where's the sine function? Well, let me see. Here it is. Times 2. And that value is 0.6577. All right. Now, how do you get theta? How do you get the angle out of that expression? Well, it's called the arc sine. And on your calculator, you'll find a button for the sine. And then usually shift sign will be what's above it. And it may be, to save space, it may be called A sine, A-S-I-N, which is arc sine. It's the converse. It's rearrange this equation, and you would say then theta equals the arc sine of 0.6577. So now, since it's already in my calculator, all I have to do is go up here and say shift arc sine, and I get 41.1 degrees. So theta here is 41.1 degrees. That's the answer. Okay? I know it took a lot of work. Now, I did that by combining two equations. If you don't feel comfortable doing that, then what you can do is solve this for D. What's the distance between the layers? And that may have been the way I did it in the worked problems. Solve it for D, then come down here to this equation and substitute D, the value D, and then solve for theta. It works both ways. Okay, that was number 1, difficult. Number 2, difficult. Okay, number 2. Now, what are we talking about? Let's see. Chromium metal crystallizes as a body-centered cubic lattice. Okay, we talked about that one in an earlier problem, actually in 2 earlier problems. If the atomic radius of chromium is 1.25 angstroms, what is the density of chromium metal in grams per cubic centimeter? Right? So read it backwards. What is the density? What are you going to need to answer the question density? You need mass and volume. Well, and not only that, the mass has to be the mass that's occupied in that volume. Right? So they have to be related. So do we know the mass yet? Well, no, not yet. We can find that out, right? We're going to have to. But how about the volume? What's the volume? Well, we sort of are on our way to it. What do we know? Let's see. And we want the density in grams per cubic centimeter. So what do we know? We know that it's a body-centered cube, and that the radius of chromium is equal to 1.25 angstroms. Okay, useful information time. How do you find the edge of the cube, right? If it's a body-centered cube, then that's going to give us the volume, right? We need the volume of our body-centered cube. Right there, and 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 there, which is equal to 2 atoms per cube, right? Now we're getting somewhere. If we know that 2 atoms of chromium are in that cube, then we can convert atoms to mass, right? We're going to need Avogadro's number, and we're going to need molar mass of chromium. We can get those right here. We can get the molar mass right there. Avogadro's number, you memorize that one. So that gives us mass. How about volume? Well, we know the radius is 1.25 angstroms. How is radius related to the edge of a cube? Because if we can find out what this distance is, then we cube it, and we got our volume. Mass and volume, we've solved the problem. So let me see. We need to find out, let's do the volume first. Body-centered cube edge equals 4r divided by square root of 3. So this is A, and A equals 4r divided by the square root of 3. Okay? So we can plug in this one. 4 times 1.25 angstroms divided by the square root of 3 equals what? Well, let's see here. 1.25, 4 times 3 square root divided. 2.887. 2.887 angstroms on that edge. Okay? Now, before we cube it, dimensional analysis will be easier if we convert this to centimeters first and then cube it. Because if we cube it first, then we get cubic angstroms, and then we got to deal with, how do you convert a linear from a cube to a cube in a different measure? It's just messy. So let's convert this to centimeters first, right? What's the relationship? Well, I gave it to you earlier. 1 angstrom is 10 to the minus 8 centimeters. Or you can chain your conversions. We know it's 10 to the minus 10th meters, and then we can convert meters to centimeters, but it ends up being that value. So this is going to be, so the volume, and then is the cube of this number, which is 2.887 times 10 to the minus 8th, right? Centimeters cubed. So let's go ahead and cube it. Let's see. Enter. Where am I? I need powers. Where's my powers? Here it is. And then I enter cubed. And that can't be right. Let me do that again. 2.887 exponent 8. There. Enter. And cube. So I plug in 3 and hit the power button. Now we're talking 2.406 10 to the minus 23rd. 2.406 times 10 to the negative 23 cubic centimeters. There's your volume. All right. Now we need mass. Right. So we got the volume, and let's put that in the equation up here. Like this equals. We'll save that for the mass. Put the volume in 2.406 times 10 to the minus 23rd cubic centimeters. Now we can erase this here. All right, 2 atoms per cell. How many moles is that? Okay, so we got atoms gone. Now we got moles. We want to convert to mass. So what's the mass per mole? Well, we have to look up chromium, don't we? So chromium looks like it's 52.00 to 2 decimal places. Okay, that gets rid of moles. So that's grams per cell. That's what we want. What's the mass in that one cell? So we just need to solve that problem. 2 enter 6.022 exponent 23 divide, right? That divided by this times that. So I get 1.727 times 10 to the 22nd grams. Put that up here. All right. So we just need to divide those two. So I got it in my calculator already. This one, let me see if the other one's there. Yep. Divide. So I get 7 point, see how many, how many significant figures am I allowed? That is a counting number, so it's infinite. Infinite. Now I keep as many as I want here. How about this one? That one's based on 3 significant figures, isn't it? So I can keep 3. 7.18. 7.18 grams per cubic centimeter. There it is, B. Okay. Any questions? It's probably about time we get on to chapter 11, don't you think? Before we run out of time. There we go. Close that up so it'll be standing up on its end. There we go. Okay, let's see. Yep, that's enough for chapter 10. Ready to go to chapter 11. All right, that's chapter 10. Now chapter 11. So I need to unshare this one and share the other one. Chapter 11. There we go. And I hope everybody can see that. Wait a minute. What did I just do? Oh, hold on. There we go. Still got chapter 11, I'm hoping. And let's change the identifiers up here. So this is going to be chapter 11. And we'll start off with the easy. Okay, let me look at my sheet here. I'm going to do the whole first page. Right. So the whole first page says 1. In a 0.1 molar solution of sodium chloride and water, which of the following will be closest to 0.1? So we're talking about the magnitude. Which one of these other units of measuring concentration are closest to 0.1? So we're starting off with 0.1 molar sodium chloride. All right. How about the mole fraction? Mole fraction. What do we need to know? We need to know how many moles of sodium chloride are in a liter of water. We also have to know how many moles of water that is. All right. So, do we have enough information? Well, let's see. Let's all right. How many moles do we have here? In 1 liter, we have 0.1 mole sodium chloride per 1 liter of water. So how many moles is a liter of water? Well, we have to assume, actually that's a liter, excuse me, that's wrong. It's a liter of solution. Okay. So a liter of solution is composed of both sodium chloride and water. So what's the mass of that? This is a very dilute solution, 0.1 mole sodium chloride. So we can say that all of that is virtually water. So that's 1,000 grams of water. And how many moles per gram of water? Well, that's 18.02, right? So we virtually have, let's see, 1802 divide into 1,000, which is 55.5 moles. So 0.1 divided by 55.5 is 1.8 times 10 to the minus third. 1.8 times 10 to the minus third mole fraction. That's a long way from 0.1, isn't it? All right. What's our second choice? Mass fraction. So what would be the mass fraction? Mass fraction. Well, it's the mass of sodium chloride per mass of total. Not times 100, just the fraction. So, what's the mass of 0.1 mole sodium chloride? Well, let's see. We need a conversion factor and a better marker. So what's grams per mole sodium chloride? Well, let's see. I've already done it. So it's 58.44 grams per mole. So 1/10 of that is 5.844 grams. Okay. And how many grams of solution do we have? Well, if it's 1 liter, it's pretty close to 1,000 grams, right? So this would be divided by 1,000, right? So what we would have is move 3 places this way. 1, 2, 3. So there's your mass fraction. Okay, that ain't it. What's the third one? Molality. No, excuse me. The mass percent. mass percent is just the mass fraction times 100, right? Because this is parts per part. That's that many parts per one part of solution. Parts per 100 would be 100 times that, right? Which would be C, then would be percent, would be 0.5844, 100 times 1, 2, right? So that's not it, right? It's not nothing. So far, we're not even close to 0.1 using these different measurements. The only one left is the molality. And E can't be right because we know that the others are not. So process of elimination, it should be molality. Well, let's see if that's true. Okay. So we can get rid of these. Okay, there we go. Now, 0.1 mole of sodium chloride per 1 liter of solution. Since sodium chloride is so dilute, we can virtually say that this is per 1 liter of water. And 1 liter of water is 1 kilogram because it's 1,000 grams, right? 1 gram per milliliter or 1 kilogram per liter, same ratio. So molality would then be 0.1 mole per kilogram of water. So molality and molarity for dilute solutions are almost identical. There's a slight difference, and maybe I actually calculated the exact in the work problems, and it's 0.1006. So it's sufficiently different than the others to claim the prize. So let's look at 2. All right, yes, 2. Which of the following concentration measures will change in value as the temperature of a solution changes? What's the key to this question? As the temperature changes, something in the concentration expression has to change, right? So what changes with temperature? If we're talking about concentration, it's units of something per units of the solution or units of the solvent, either way. So what do we have? Well, mass percent is mass per mass. Does mass change with temperature? No. Mole fraction. The number of moles change with temperature? No. Moles are an expression of numbers of things. And changing the temperature doesn't change the numbers, right? You'd have to create or destroy matter to do that. Molality, right? What's that expression? Moles per kilogram, right? Moles and kilograms, they don't change with temperature. Molarity, moles per volume. There's your key. Volume changes with temperature. So D's your answer. How about 3? Which of the following chemical or physical changes is an endothermic process? Remember, relative to the system, endothermic means energy into the system. So when water evaporates, what has to happen? You got to put energy in, right? You got to make the water molecules farther apart, and that takes energy. So A is the answer, right? E says none of these, and A is correct, so it's got to be it. Combustion of gas is exothermic. I mean, anybody around an exploding gas can will tell you that. The mixing of sulfuric acid and water, anytime you mix strong acid and water, you're going to get exothermic reaction. Right? That's why the rule of thumb, do as you oughta, add acid to water. You add acid to the water, not the other way around. Because when you get all that heat developed from the acid going into solution, if you've got a lot of volume of water at room temperature, then it will absorb the heat. But if you put water into acid, then all that heat is concentrated in that little bit of water, and it flash evaporates. And that's what spatters acid in your face. That's exothermic. The freezing of water. When water freezes, it goes from liquid to solid. More stable system now has to give up heat in order to do that. So that's exothermic also. A has to be the answer. How about 4? Which statement about hydrogen bonding is true? Right. So from the looks of the selections, we just need to find one of them that's true. Hydrogen bonding is this is A. Hydrogen bonding is the intermolecular attractive forces between two hydrogen atoms in solution. No. What do you need for hydrogen bonding? You need hydrogen. And then you need some select electronegative atoms. Oxygen's a good one. Nitrogen's a good one. I even think sometimes sulfur is a good one. And fluorine also. Problem with fluorine is, once you've bound fluorine to hydrogen, that's it. You got no other options, because fluorine won't bond to anything but one bond. Right? So HF is the only choice you got there. But for the others, you can have multiple bonds. That means this could be, for instance, oxygen, hydrogen. This could be CH3, methanol. Or it could be ethanol. You can have hydrogen bonding sites on a large molecule. So A is wrong. It doesn't work that way. You've got to have the covalent bonding between an electronegative atom and hydrogen before you can do that. And then what you get is like that. Then that oxygen will bond to a hydrogen from some other molecule weakly, and then this one will bond to the oxygen for another molecule. Okay, B. The hydrogen bonding capabilities of water molecules cause this molecule, which is a hydrocarbon, butane, to be more soluble in water than CH3OH. That's wrong, right? Water hydrogen bonds, methanol can hydrogen bond. There's a very strong interaction. This is a non-polar molecule. It's symmetrical all around. So it's not likely to bond with water at all. B is false. C, hydrogen bonding of solvent molecules with a solute will not affect the solubility of the solute. I mean, alarms ought to be going off in your head now. That's just patently false. Hydrogen bonding contributes to the solvation of molecules as long as they're available. Right? If you've got hydrogen bonding available for your solute and the solute responds to it, it's an ion or it's a polar molecule, or even better, if it's capable of hydrogen bonding itself, you have a much better chance of forming a solution with that solvent-solute interaction. So C is false. D, hydrogen bonding interactions between molecules are stronger than the covalent bonds within the molecules. If that were true, what would happen? What if the intermolecular forces holding molecules together were stronger than the covalent bonds holding their atoms together, what would happen? Those molecules would be ripped apart, right? So that can't happen. Not unless you expect it to happen. If you want it to happen, the hydrogen bonding is not stronger than covalent bonds. Covalent bonds are much, much stronger than hydrogen bonds. E, hydrogen bonding arises from the dipole moment created by the unequal sharing of electrons within certain covalent bonds within a molecule. That's as true as you can get without being more specific. So E has to be the answer to 4. Okay, let's see, what am I doing? 5, okay, I'll do 5 also. Which of the following favors the solubility of an ionic solid in a liquid solvent? A, what about A? A large magnitude of solvation energy of the ions. So what does that mean? Solvation energy is the energy that's given up when the free solute molecules interact with the solvent. Remember those 3 stages of solution. Right? The first one is solute separation, where you pull the solute apart. You break the bonds that are holding the solute molecules together. That takes energy. So this is a negative value for delta H. This one, solvent separation. That's also endothermic. You got to make a hole for these molecules to go into. And this one is solute solvent interaction. That one's positive. Now, in other words, you get energy back. So if the attraction between solute and solvent is very strong, you get a lot of energy back. And a large magnitude of solvation energy, which is this one, favors the solubility of ionic solids in a liquid solvent. That's true. How about B? A small magnitude of lattice energy of the solute. So what's the lattice energy for the solute? Lattice energy is, well, we're talking about an ionic solid, right? So we have a positive and a negative, right? There's your ion, and this is a solid. Well, actually, the lattice energy is the other way around. If you have this one as a gas and this one as a gas, then it makes this one as a solid. The amount of energy that you get out of that reaction when it comes together, when these two come together in that forming that lattice, if that's small, what does that mean? Well, if you didn't get a lot of energy back, then it doesn't take much energy to break it up either, right? So that means this part will be very small. That would favor formation of the solution. because you don't have to put much energy in to get them apart. A large polarity of the solvent. Polar ion interactions are usually very strong. That's why most, but not all, ionic compounds are soluble in water. I should say most. I should say a lot of them are. For that reason, it favors the formation of a solution, that polar interaction. So actually all of the above are true. A through C is true. That makes D the correct answer. Okay, I got a half hour left. Let's see if I can do this. We're just getting off the first page. How about, okay, 6 is one that should have been placed in the moderate or the difficult section. And I hope I can explain it so that it makes sense. And following on number 5, our brain should be geared up for the logic that's involved in number 6. So, what do we have? Well, solid potassium fluoride has a lattice energy of minus 804 kilojoules per mole. So remember what I described, lattice energy, as the individual gaseous potassium and fluoride ions come together to make a solid, they give up energy. That's the lattice energy. They have a heat of solution in water of minus 15 kilojoules per mole. Right? So that's overall. H1, H2, H3, all three of them together give you delta H of solution, and that's the value here, minus 15. All right? Rubidium fluoride has a lattice energy of minus 768, similar process, and a heat of solution of minus 24. Which salt forms stronger attractions with water? Okay. On the surface, you would think, well, look, there's more energy given up here for rubidium fluoride, so we would expect, yeah, rubidium fluoride is a stronger attraction. But that's not necessarily true, because you have to look at the individual steps of the process. So let's do that. So let's put that back up here. This is, what did I say, number 6. So if we have the delta H of solution, which is given for each one, we know that one, and the delta H1 is has to do with the lattice energy of each of them, right? And then we have delta H2 and delta H3. This is the solvation energy. That's the one that we're after to answer this question. Which salt forms stronger attractions? That one right there. Because this one, you split the water apart, right? How much energy does it take to pull the water molecules apart? Well, it's the same for both of them, isn't it? Right? It's not going to be any different. So if we know this one right here, then we can say the difference between the two is based on that, since this is the same for both, right? So we just need that term. And we're given this term and that term, right? So for potassium fluoride, this term is what? Minus 15 kilojoules. Right? And this term is not minus 804, because minus 804 is when you're going from gas to solid. when you're breaking the bonds and going from solid to gas, it's the other way around. You have to put energy in. So instead of negative, which means getting energy back, it's a positive. You're putting energy in. So it's 804 here plus 804 kilojoules per mole. Plus this delta H 23. Okay. For rubidium fluoride, its overall heat of solution is minus 24. And this value is positive 768. Okay, so now what we have to do is solve for these two. Right? So for KF, the delta H23 is equal to, put this one on that side, becomes a negative. So now this is a negative plus a negative, which makes a bigger negative, which would be, let's see if I can do this in my head, 800 negative 819 kilojoules per mole is equal to this value here. So as the solute solvent begin to attract one another, they give up that much energy, which means the bigger the negative number, the stronger the attraction. And this one then would be that negative and this negative, which should be, let's say, 2, 9, 7. Right? So which one has the stronger affinity for water? That one right there. So out of the possible multiple choices, KF, since it has a larger lattice energy, no, that's not the whole answer to the question. Rubidium, since it has a smaller lattice energy, no, has nothing to do with the lattice energy per se. It has to do with the calculation using the lattice energy. So KF is the stronger attraction since it has a more negative heat of hydration. This is known as the heat of hydration. When the salt combines with the water, that's called hydration. Okay, so I guess we have to define terms too. And that's one of the reasons I wanted to focus on this problem, because some of these terms we hadn't covered yet. Right? Maybe they're in the book, maybe not, I don't remember. But this is heat of hydration right here, that calculation. Well, no, I take that back. That's heat of hydration. But since the combination term has that value is the same for both of them, then we can infer that the heat of hydration for KF is larger than the heat of hydration for rubidium fluoride. Okay. Coming down to the wire and running out of time, so let me see, what's 7? Use the following drawing of a gaseous solute in equilibrium with a solution to help answer the question below. Which of the following statements are true when the piston is pushed downward? Well, there's a law governing this. Remember which one it was? Henry's law. The concentration of gas dissolved in a liquid is proportional to, with our proportionality constant, I forget what symbol was used. Normally we use a C for constant, but this is concentration, K. K times the vapor pressure, the pressure on the vapor. Okay, it's proportional. So that means if the pressure goes up, the concentration goes up in the liquid. So what's happening here? Well, let's see. Play around with annotation a little bit. Okay. What happens when we push the piston down? The pressure increases, right? So not only are we using Henry's law, we're using Le Chatelier as well, because we assume that before we push the piston, we're at equilibrium, right? It has a certain vapor pressure. So if we push down right here, if we push down on that, then we're decreasing the volume, and the piston might be down here now, right? Less headspace for the molecules, so the pressure goes up, which means what? The concentration of the gas in the liquid increases. Now, for this one, we're assuming that this is this is different. The solute gas is different than the solvent, right? It's not water vapor being forced back into its liquid state. It's a gas being forced into solution, like carbon dioxide in your pop bottle being forced into aqueous solution. So we increase the pressure and we get a higher concentration of gas in solution. So let's see which one of these fits. This will cause the pressure of the gas to increase and the concentration of the dissolved gas to go down. Just the opposite, right? The concentration will go up. B, this will cause the pressure of the gas to decrease. Well, that's false right there. The pressure is going to go up, right? Boyle says if you decrease the volume, the pressure goes up. So C, this will cause the pressure of the gas to increase, true, and the concentration of the dissolved gas to go up, true. C is your answer, right? We don't have any other weird answers below there. You found your answer, you can stop. It's C. All right, let's see. Oops, I need my mouse back. 8, okay. Oops. Let's see. I'm gonna have to use the eraser. Hold on a second. There we go. Now get my mouse back. All right. 8. Which of the following correctly states the relationship between temperature and the solubility of a substance in water? What do we know about the solubility of substances in water? Well, it depends, right? If it's a solid and it's an ionic solid, what's the most common response to temperature? Solubility goes up as you increase the temperature, but it doesn't happen to all of them. Do we know why? Well, there's some theories out there, but we cannot predict its solubility, right? We have to measure the solubility first and then propose an answer to it. But we can't predict beforehand whether a certain solid will go into solution with an increased temperature. How about gases? Well, we know the gases decrease solubility as the temperature goes up. We do know that one. So let's see. Which of the following correctly states the relationship between temperature and solubility? The solubility of a substance in water increases as the temperature rises, especially for gases. We might have been halfway there if we'd have left out the gas reference. We know that it won't work for gases. Gases are exactly the opposite. How about B? The solubility of a substance in water decreases as the temperature rises, especially for ionic solids. Well, that's false too. You can't really predict. Usually, the solubility goes up with temperature, but not always. The solubility of a substance in water with temperature cannot be accurately predicted, especially for ionic solids. That's absolutely true. That's the best answer yet. And since C is correct, then E can't work, right? Because we know A is false, and D is probably false too. Okay. Hold on a second. The solubility of a substance, this is D, in water decreases as the temperature lowers, especially for gases. Now, that can be interpreted a couple of ways, but if we read it literally, first, the solubility of a substance in water decreases as the temperature lowers. Well, that's true for some solids, not for all, and it's true for gases. So the caveat there is that the outliers disprove D, because some of them increase solubility with decreased temperature. So that makes D false. If you don't stop and look at it carefully, break it apart, then your tendency is to say that D is true, but it's not. Not the whole statement taken together after you put the pieces back together. Okay, let's see, what's next? Skip down to 10. Okay, a solution contains 1 mole of A, liquid A, and 3 moles of liquid B. And this solution has a vapor pressure of 314 torr at 25 degrees. At 25 degrees, liquid A has a vapor pressure of 265, and liquid B has a vapor pressure of 355. So what we're saying here is we're dealing with Rayleigh's law, right? Vapor pressure based upon well, temperature, but concentration, mole fraction. The mole fraction of the solvent, if it's volatile, and the solute, if it's non-volatile, is the ideal or simple Rayleigh's law. But here, the evidence is that liquid A has a vapor pressure and liquid B has a vapor pressure. So we have a modified Rayleigh's law. So what does that look like? That looks like for, where are we, 10. Modified. You've got total pressure is due to both the solute and the solvent, both of the liquids in the mixture. So you have to account for both of them. So the mole fraction of A, is that how they're calling it? A and B, yes. The mole fraction of A times the pure vapor pressure for A plus the mole fraction of B times the pure vapor pressure for B will give you the total pressure. Now, one thing we know is that number and that number have to add up to 1. So if this one goes up, that one goes down. That one goes up, this one goes down, vice versa. One thing we also know is if we calculate, if we measure the total pressure here, and then we calculate these terms based upon their mole fractions, then if the solution is ideal, that total will equal to the measured value. Okay? If this total is greater than that one, then the deviation is said to be positive. Right? Remember the hump curve. If the total here is less, no, if the measured is less than the total, excuse me. If the measured value is less than the calculated total, it's negative deviation. If the measured is greater than the calculated total, then it's positive. Okay, so let's see what we've got here. Measured, the solution has a vapor pressure of 314 and the temperature is constant. So this is 314 torr. Remember what a torr is? 1 torr is 1 millimeter of mercury, right? So 760 torr is 760 millimeters of mercury is 1 atmosphere. So what are the vapor pressures for A and B? 265 calculated and 355 calculated. So add these together. What do you get? Well, look, 355 over here and 314 there. If you add that, it's definitely going to be bigger, right? So what's the deviation? The deviation is negative because this one is less than the total. If the measured is less than the calculated total, then the deviation is negative. And your plot then is going to be below the line. It's negative. So the answer to that one, in the interest of time, is B. This solution exhibits a negative deviation from Raoult's law. All right, 12. This one should be fairly simple. All right, you got a slice of cucumber, or a cucumber, is placed in a concentrated salt solution. Okay. So let's say we've got our cucumber slice here with its seeds here and here and here. And we put it in a salt solution that is, let me see, let me get my terms correct, concentrated. All right. What kind of problem is this? Osmotic pressure. The osmotic pressure forces water out of the cucumber and into the salt solution. Why? Because the concentration of water inside the cucumber is higher than it is in the concentrated salt solution. And every cell in that cucumber is a semi-permeable membrane, which will only allow water to pass through it. So it's going to go from a high concentration of water to a low concentration of water. All right. So that means the mass of the cucumber will shrink and the volume will shrink. And the answer that satisfies that, water will flow from the cucumber to the solution. There's your answer. When will change not occur? When the concentration of salt out here is isotonic with the cytoplasm inside the cell. Then there won't be any movement at all. If this is distilled water, what will happen? Water moves into the cucumber and the cells start to explode. Okay, that was 12. 13. Osmotic pressure depends on all but which of the following? So we'll pick it up from there, talk about osmotic a little more. How do we measure? Well, What's the formula for osmotic pressure? How about that? Pi. Pi is our term, our variable for osmotic pressure, and it's equal to what? Well, it's proportional to the molarity of the solution, and it's got a constant there, gas constant, right? And it's got temperature. And what else? It's got a correction factor. The Van Hoff correction factor. And that's for solutes that either break up into more parts when they go in, or sometimes they may pair when they go in, right? In that case, the I would be in a smaller than 1. If they break up perfectly, which is probably an aqueous dilute solution, then I would be 1. But if they're like sodium chloride and they break up into 2, ideally the I would be 2, or calcium chloride would be 3, or sodium or ammonium phosphate would be 4. But let's answer the question. What is the osmotic pressure dependent upon? Is it dependent upon atmospheric pressure? It depends on all of these except 1, or E says none of these. Right, so you've got that fly in the ointment there. Is there atmospheric pressure anywhere in here? No, you can't count the constant. I mean, it has an atmosphere term in it, but it's not dependent upon atmospheric pressure. It's dependent upon molarity, right? There it is, B. Temperature, C. Ratio of moles of solute to solution volume is another way of saying molarity, right? So the one that it's not dependent upon is atmospheric pressure. All right, so let's go to, what's next? 6. No, I'm sorry. Turn the wrong page. 14. All right, this is just memorization, right? Colloids can come in different phase combinations, right? So if we just put them up here, let's see. A is an aerosol. B is a foam. C is an emulsion. D is a sol. And E is a coagulate. All right. So let's eliminate the stupid one. Which one is not a colloid? That one. That's what colloids do when you destroy the colloid. You coagulate. So this one's not a colloid. These others are colloids. But it depends on the combination, right? So what's shaving cream? Well, let's see. It's a liquid solvent, and what's in it? A gas. A gas and a liquid is shaving cream, right? So let's go down through these. An aerosol is a liquid or solid in a gas. So it's just the opposite. A foam is a gas in a liquid. So there's your answer right there. Emulsion is a liquid in a liquid, and a sol is a solid in a liquid. Okay, like Jello, right? All right, so that was 14. We can go to moderate number 3. Okay, I'm past time. But we're almost there. Moderate 3. All right. So let me scroll down. Moderate 3. Here we go. A 0.2 molar solution of a solute. So we're given that concentration. .2 molarity of solute X in benzene displays an osmotic pressure given by the formula pi equals 0.1 RT. Which of the following is most likely to be the case? All right, let's break this up. Let's say, what are these terms saying? Right? That one is the same from the osmotic pressure formula. This one's the same. That was the same. This one is a combination of this one and that one. Right? So, if we know the molarity of the solution is 0.2, but we know this is equal to 0.1, then 0.1 is equal to this times that, which is equal to that times 0.2. Yeah, let's do it this way. There you go. Then that means the difference between these two is due to I. And what is I? Solve for I. 0.1 divided by 0.2 is 0.5. It's 1/2. 0.5 is equal to I. So now how could you get less than 1 for this solution? The value for I. Well, we know how to do it if the compound breaks up into more parts. So the other direction has to be operating here. You have to take the parts, when you put them in a solution, they form pairs, or maybe even more than that. But they have to pair up somehow, group together. So in that case, X has to exist in benzene as what? Once it goes into benzene, it can't be X again. Otherwise, I would be 1. So it must be a pairing. X exists in benzene is X2. Okay? That's the only explanation. If it dissociated into 2 particles, I would be 2. And the solution strongly deviates from ideal behavior. Well, yeah, but the best answer is B. It's better than D. And like I always say, when confronted with more than one choice, pick the best one. All right, that was 3. Okay, I'm going to do 4 and 5 together because they're based upon the same calculation, I do believe. Yeah. So we can save a little time there. So we'll do 4 first. All right. Which of these solutions, scroll down, which of these solutions, 0.1 molal sodium chloride, 0.15 molal glucose, 0.1 molal calcium chloride would have what? Which would have the highest vapor pressure and which would have all the lowest boiling point, right? So let's write them up here. 0.1 molal sodium chloride, 0.1 molal sodium chloride, and 0.15 molal glucose, and 0.1 calcium chloride. 0.1 calcium chloride. Okay. So what we need to know about these is what is the molal concentration of the particles in solution. Right? This one breaks apart. Right? So it yields 0.2 molal. This one doesn't dissociate. And this one breaks up into 3 parts. Okay, now we have the molal concentration, and we know how things behave relative to their concentration. For the highest vapor pressure of the solution, you need the lowest concentration of solute, because increasing the concentration of a non-volatile solute decreases your vapor pressure. Okay. So this one is the lowest, should give you the highest vapor pressure. So that means it's got to be B or D. How about the lowest boiling point? The lowest boiling point also has the lowest concentration, right? When we say boiling point elevation, that means the highest concentration will give you the highest boiling point. But if the lowest, then the lowest concentration will give you the lowest boiling point. And that also is glucose. So D is the answer to this one, because both conditions, highest vapor pressure, lowest boiling point, dependent upon the lowest concentration in solution. How about 5? We're using the same 3. So now we're looking for different conditions. Lowest vapor pressure, isn't that what one, Roman numeral 1 is the same as before, isn't it? Yeah, no, lowest vapor pressure. All right. Lowest vapor pressure would be the highest concentration of solute. So the lowest vapor pressure would be calcium chloride. But the lowest boiling point would again be the lowest concentration glucose. So this would be 0.1 molar calcium chloride and 0.15 molal glucose. So that makes C the answer for 5. Now to difficult. And we're almost there. Difficult. Oops, that's not 5. Which is, when is it? Number 2. So let me scroll down to 2 in the difficult section. There we go. Okay. A solution is prepared from 53.8 grams of a non-volatile, non-dissociating solute. Okay, so let's write what we know up here. Let's look at the question first. What is the molar mass of the solute? That's our end game. Molar mass, or molecular weight, as I abbreviate it. And we need to know the mass and we need to know the moles. Right? So now we can go back and say, what are we given? 53.8 grams of a non-volatile, non-dissociating solute. So the mass of the solute is 53.8 grams. Right? And then it's dissolved in 85 grams of water. So the mass of the solvent is 85.0 grams of water. Okay? Now we're going to look at the vapor pressure of the solution at 60 degrees centigrade, Celsius, is 132 torr. So we've got the solution vapor pressure is 132 torr. But the ideal pressure of water, I mean, the vapor pressure of pure water is 150 torr at that temperature. Right? So the temperature doesn't change. We don't have to worry about the temperature. What's the molar mass of the solute? All right, now let's look at our data. We've got the mass right here. What we need is the number of moles of the solute. So, what are we saying here? The vapor pressure, we're dealing with Rayleigh law. The measured vapor pressure here, this pressure of solution is equal to the mole fraction of water times 150 torr. Right? That's the pure. This is the mole fraction of water, and that's the measured. Right? So we can find out the mole fraction of water. So what's the mole fraction of the solute? It's 1 minus that one, isn't it? The mole fraction of our, well, let's call it X. The mole fraction of X is equal to 1 minus the mole fraction of water. Okay? Okay. So what do we need to know? We need to know the moles of water, definitely. We need to know the total moles. Well, if we say we're going to calculate the moles of water here. All right, so that's 18.02. So let's do that one first. Moles of water. We know we're going to need it. We can't do the mole fraction unless we know how many moles there are. That's is that right? Let me try that again. 85, enter, 18.02. Yeah, 4.717. Okay. And the moles of this one, let's just call it X. X moles of X. X moles of X. Okay, so we know, let's see. All right. So one other thing that we also know is that we have an equation. Let's see. Where is it? Ah, okay, here we go. We've got an equation in one unknown right here, right? 132 equals this times that. So we can find out what the mole fraction of water is, right? Mole fraction is this divided by that. So the mole fraction of water equals 132 divided by 150, which is 0.880. Okay. All right. So I'm going to need to erase some of this. We know the mole fraction of water. Right, so I can leave that there and erase this. Now, what's the mole fraction of this one? Well, it's the moles of that one, X. Mole fraction of X equals X moles divided by X moles plus moles of water. Right? And this value is equal to what? 1 minus 0.880. So now what do we have here? We've got an equation in one unknown. We just resolved this one, which is 0.12. Right? And then we resolve this one. So, algebraically speaking, in interest of time, we say if this expression is equal to that number, then we take this expression, multiply it by that. That gives us 0.12 times X moles plus 0.12 times that number on one side and X moles on the other side. Then we take 0.12 and bring it back on this side, subtract it from 1, which is actually 0.880. Let's just do that. Talking about it's not making it any easier. Right? So now we got this equal to that. So that means X is equal to 0.120x plus 0.120 times 4.717.12 is 0.566. 0.566. That's just a number. Right? So then we can bring this one on that side, which actually brings us back to 1 minus this is that, 0.880. X equals 0.566, and X equals this one divided by that one. And let's see what we got. 0.643. So this one is 0.643, and this one is 53.8. 0.8 grams. It's moles. So 53.8 53.8 divided. I get 83.6 grams per mole. That's E. Okay. So this is one of those complex problems that appears on the surface to be insurmountable. So you break it down by first finding out what's the question. The question is, what's the molar mass of the solute? You know what you need to find the molar mass. You need its mass and you need its moles, right? So what have you already got? You already got the mass. So now you need to focus on the moles. And with this information, recognizing that you have changed the vapor pressure of the solution relative to the pure solvent tells you that you're dealing with Raoult's law. Okay, we're going to look at, let's see, where am I? Lost my place. Number 4. All right. Now this one, let me see, how many do I have to go? That's it. All right. Maybe I can finish by 12:30. All right, number 4. Okay. What's the question? Number 4. Calculate the percent by mass of sugar in the original mixture. So that's what we're looking for. Percent mass of sugar. Now, what are we given? We're given that it's a mixture of sugar and table salt, and that's the solid. Right? And the total of that mixture is 10.4 grams. So the mass total is 10.40 grams. All right, that's sucrose plus sodium chloride. All right. When this mixture is dissolved in 150 grams of water, so we have the mass of water is 150 grams. The freezing point is found to be minus 2.24. So freezing point is minus 2.24 degrees Celsius. All right. So let's see. What are we dealing with here? All right. Freezing point depression. Right. Freezing point depression is equal to, remember, our correction factor times the molality of the solution times the freezing point depression constant for water. All right. So that should set off alarms. As Sucrose does not dissociate. Sodium chloride does. But the other trick is that this term, this change in temperature, is due to both factors acting simultaneously. So this is also equal to I molality of sucrose times K plus I molality of sodium chloride times K. You can factor those out. Let's see. In other words, this change in temperature is additive. We know what the temperature, change in temperature is. It's 2.24 degrees C, without the negative. We only are interested in the change of temperature. We know that for this one, that value is 1, and this value is 2. Right? We know that the K is a constant. And let's see, it should be part of useful information. Yeah. Freezing point depression, 1.86. 1.86 degrees C per molal. All right. So now the variable in all of this, we actually have two variables. One is molality of sucrose, molality of sodium chloride. All right, so now we got to tease out that information. Okay, so let's take these two terms and say, what are they equal to? The molality of sucrose. It's moles of sucrose per kilogram of solvent. So if you got 150 grams of water, how many kilograms is that? 1, 2, 3. 0.15 kilograms. Okay, and the molality of sodium chloride is equal to the moles of sodium chloride per 150.15 kilograms. Okay. All right. Excuse me. Now, let's substitute this expression in here and this expression in here. All right. So I need to erase some things, of course. We've used this already. We need to hang on to that. So we'll leave that one there. We've used this one. And we've used this one. So I need to start writing this equation over here, incorporating these values. So this 2.24 change temperature is equal to, well, 1 times the molality, so we don't have to put that in there, of sucrose. So we have N of sucrose divided by 0.150 kilograms times the K, 1.86 degrees C per molal. And then we add this one, which is 2 times moles of sodium chloride per 0.15 kilograms times 1.86. There we go. So now we got that done. And then we can erase this part. All right. So now, let's rearrange this equation so that we can get everything that's common on this side back on this side. So what can we do? It's called, in algebra, it's called factoring out. So we factor out this value because it's the same for both terms. Now that becomes from the numerator to the denominator. 2.24, and then we're going to divide by 1.86, both sides. We also have in the denominator 0.15. So now it's in the numerator on this side. Now what do we have left on that side? Now on this side we have moles of sucrose plus 2 times the moles of sodium chloride. And this term reduces to, let me do a quick calculation, 2.24 and 0.15 divided by 1.86 is 0.1806 is equal to that value. Okay. We need to know, let's see. We need an expression for moles of each one. We're going to need the molar mass, right? Because what are we looking for? Mass percent. So we need to know the total mass, which we do, and then we need to know the mass only of sucrose. That's it. So if we let's say, what is moles equal to? Right? Moles of sucrose would be, what's the molar mass of sucrose? Well, let's see, I've calculated it already. The molar mass of sucrose is 342. 342 grams per mole. And sodium chloride is 58.44 grams per mole. So how do you convert moles? Well, what does that mean? Grams per mole. If you have mass and you multiply it by moles per gram, right? You get moles. So moles then is equal to, let's see, this value here is like 342. So if we say moles divided by, no, that's not working. Let's look at the units of measure. That'll fix it. What is this equal to in terms of mass? If we have mass, say, let sucrose be X grams of sucrose. If we divide that by the molecular weight, which is grams per mole, and this is grams, then the grams cancel and leaves us with moles. So what we need is this expression is equal to X divided by 342 grams per mole. That's what that's equal to. This one is 2 times whatever moles of sodium chloride, which would be, well, we have to do this in terms of X. So if we've got X grams out of that number, what's left over? Sodium chloride. So sodium chloride is 10.4 minus X divided by 58.44. Okay. Now we've got an equation in one unknown. You just need to solve that equation, and you find that X is 5.60 grams. And the answer to this question is 5.60 divided by 10.4 times 100 equals 53.8%. Okay, so I was hurrying up, but do that calculation yourself. Solve for the X, and then you can make this transition to the answer. I know that took a long time, but there are several tricks in there. The first, most important one is to say, what do you need, right, to calculate this percentage? Well, you need the mass of sugar, and you need total mass. You've got the total mass, so you need the mass of the sugar. But with the data that you're given, the freezing point depression, that's all in terms of moles per kilogram of solvent. So that's where you have to relate the moles to grams right here. Okay, we're done. Let me stop the share and see if there are any questions before I, let's see. Yeah, I normally host a lab tutorial, so it'll have to be right after this. As soon as we close here, I'll open up the, I'll go to Chem104 and click on the Zoom there and open up that meeting. And then if you have any lab problems, we can talk about them there. But if you have no comments or questions, we can call it a day for this class, and we'll pick up with chapter 12. 10, 11, 12, yeah. Chapter 12 next Monday, due date for exam 1.